Good evening. We are now coming up to the best part of the Perseid meteor stream. And between now and the middle of August, we're certainly going to see a large number of meteors or shooting stars. But first of all, what exactly are they? Well, a shooting star certainly isn't a star. It's a tiny particle going around the sun in the same way that we do. And so long as it stays clear of us, we can't see it. It's too small and too faint. But if it dashes into the top part of the Earth's air, it rubs against the air particles and becomes so hot that it burns away in the streak of light that we call a shooting star. And here is a picture of one. It's that trail over to the left-hand side of your screen. The longer trail over to the right is actually the trail of an artificial satellite. But meteors come in two types, shower and sporadic. Sporadic meteors are solitary travelers, and they may appear from any direction at any moment. But shower meteors don't. The meteors in any particular shower seem to come from one special point in the sky known as the radiant. And the August meteors come from a radiant in the constellation of Perseus. That's why we call them the Perseids. Here's an all-sky picture taken by Stan Armstrong, and if you know your star patterns, you will see there to the upper right the W of Cassiopeia, and below that, slightly to the right of center, you will see Perseus. And that's where the radiant of the August meteors is. And the meteors seem to come from that part of the sky. Not necessarily in Perseus, but from that one particular point, as you can see there. And this is purely an effect of perspective, because they're really going through space in parallel paths. And I think the best analogy I can give you is that of a motorway. And here's a picture I took some time ago, standing on a bridge overlooking a motorway. And although those lanes are parallel, they seem to meet at a point near the horizon, which you can call the radiant of the lanes. They really are parallel, and in the same way, the parallel paths of the meteors seem to make them radiate from one particular point in the sky. Now, at this stage, I'm delighted to reintroduce one of our meteor experts, Dr. John Mason. Welcome back, John. You know, because meteors can sometimes be very bright, I think people are surprised at how small they really are.
I think that's true. The space between the planets is filled with minute particles of dust, and I have here a dish of salt, and most of those particles are smaller than that. And something the size of these rice grains would produce a meteor easily visible to the naked eye when it entered the atmosphere. And it's important to point out the difference between those tiny dust particles and large fragments of rocky material known as meteorites. I have here a fragment of a meteorite which fell on Christmas Eve 1965, the Barwell meteorite. And meteorites are debris that come mainly from the asteroid belt between the orbits of Mars and Jupiter. The tiny particles of dust that give rise to meteors are from comets. They are the debris of comets. And although they're very small, they appear extremely bright because they're travelling extremely quickly. Those tiny particles enter the Earth's atmosphere at speeds of between 11 and 72 kilometres per second, so they have an enormous amount of energy. And as they enter the very rarefied upper layers of the atmosphere, they hit the particles of air up there, and they excite them and make them glow. And this produces a trail of what we call ionization. And it's that tube of ionization that we see, not the actual particle itself, that is the phenomenon known as a meteor trail.
So what the process of ablation? I mean, you get the same kind of thing with a spacecraft re-entering. Only in the case of the spacecraft, when the spacecraft is left, at least we hope it is, and the meteor actually destroys itself and ends its journey in the form of very fine dust.
That's right. Of course, with a spacecraft, the heat shield burns away and saves the interior of the spacecraft. With the meteor, the entire tiny particle is incinerated at a height usually over 80 kilometres above ground level.
Well, we are now coming up to the best time of the year, the Perseid shower. But of course, in the past, there have been showers more spectacular than the Perseids.
Oh yes, in the last century we had some superb meteor displays. In the years 1833 and 1866, there were some spectacular meteor storms when rates reached many thousands of meteors per hour. Here we have a woodcut of an old meteor storm, and because these meteors appeared to come from the constellation Leo, they became known as the Leonids. There were no Leonids seen in 1899 and 1933, but in 1966 the Leonids came back on the night of November the 17th, and here's a picture taken on that night. Observers in America recorded rates of over 100,000 meteors per hour. It must have been really spectacular.
But here, of course, we saw nothing at all, and I remember that very vividly because we did a Sky at Night program about it and asked various people to keep an eye out for Leonids. We had over 10,000 replies, and because it was a brief storm and occurred in our daylight, no one here saw anything at all, and I still have some of those letters. But of course, the Leonids will be back. Meanwhile, We said that meteors are cometary debris, and we do know the parent comet of the Leonids.
We do indeed. Comet SwiftTuttle, which returned in 1866, has a period of about 33 years, and we know that is the comet responsible for producing the stream of dust that produces the Leonid meteors. But the link between comets and meteors was really firmly established about 130 years ago with a comet called Biela's comet. Now, Biela's comet was a short-period comet seen in 1845 when it split into two, as shown here. This is a drawing by Secchi. And 7 years later, in 1852, it came back again. The two components were further apart, and it was never seen again. But in 1872 and 1885, really spectacular meteor storms were seen coming from the constellation of Andromeda, and those meteor storms we know are linked with Biela's comet. So the link between comets and meteors was firmly established. And if we look at what a comet is, we can see where this dust comes from. A comet consists of a tiny dust and ice ball, no more than 20 kilometers across, orbiting round the sun, usually on a very elongated path. When it's a long way from the sun, it's so cold it's completely frozen. But as it comes closer in, the surface gases start to boil away, the dust particles are pulled out, and it develops a dusty halo around it called the coma, and of course the spectacular tails. Here's Comet Bennett, seen in the spring of 1970. You can see the dust tail curving up towards the top and the narrow gas tail stretching out towards the bottom. And of course, the solid part at the centre of the comet, the nucleus, is where all this material comes from. We got a really good close-up view of a comet nucleus in 1986, when the European probe Giotto flew close by. And here we can see a superb image showing the nucleus of Halley's comet as the dark patch towards the bottom right, and the dust fans stretching out towards the left. And those dust particles will actually spread into the region immediately around the comet. Now here we have a view of Comet Halley, and you can see the head of the comet at the left, and the fans of dust particles radiating out to the top and to the right of the picture. And those dust particles have orbits very similar to, but not quite identical to that of the comet. And they move around the orbit slightly ahead of and slightly behind the comet. So that as the comet goes round and round its orbit many times, the dust particles spread out further and further from the comet, until eventually, after many hundreds of revolutions, the dust particles spread all the way round the orbit, and we get a meteor stream formed. Now, the very largest of these particles can, on rare occasions, be seen. The particles emitted on the side nearest to the sun, if they catch the sunlight at a preferential angle, can be seen as a spike or anti-tail pointing out of the front of the comet. And we had a marvellous example of this in 1957, Comet Arend-Roland, and you can see the spike there out to the left of the picture.
I'm not likely to forget Arend-Roland. That was the subject of the very first Sky at Night programme, April 1957, and how long ago that seems. I'm afraid Arend-Roland won't be back, but frankly, it was more spectacular than Halley's comet was last time round.
Yes, that's right, it is. And of course, it's also worth noting that although all comets produce these dusty trails behind them, we only see the meteors from those dusty trails if the Earth happens to pass close to the comet's orbit, through one of the nodes, the points where the Earth's orbit and the comet's orbit intersect. And as the Earth goes round its orbit once per year, if it goes through the stream, we'll just see a display of meteors from that comet. Now, meteor showers are of various ages. When a stream is very young, the dust particles are still very close to the comet. And one example of that, of course, is the Leonids. Now, as the particles from the Leonid comet go round close to the comet, you can see here the dust is fairly concentrated in front of and behind the comet itself. And as the comet goes round its orbit once every 33 years, we will only see meteors from the shower when the comet is close to the sun. So, for example, we saw meteors in 1966, and when Comet SwiftTuttle returns again in 1999, well, we may get another spectacular display on November 17th. I just wonder.
We'll certainly do a Sky at Night programme about it anyway.
And of course, another example of a really young meteor stream is that due to Comet Jacobi-Nizina, only discovered early on this century. It's a short-period comet, but it has produced spectacular meteor storms. Here's a negative picture of Comet Jacobi-Nizina. The comet is a smudge towards the left. In 1933, and again in 1946, Jacobi-Nizina produced very high meteor rates. And much to everybody's surprise, in 1985, when the comet came back again, very high rates were seen. Here's a graph which I obtained myself using radio methods to actually see the meteors. Because as you can see, the peak occurred at about 9:30 in the morning, during daylight hours from Britain, and it was left to observers in Japan to actually see the meteors themselves. Now, you can actually see meteors using a radio telescope, and I have a telescope of my own, and I have brought one of the aerials into the studio. And this is tuned for a frequency of 50 megahertz. I have another aerial in my back garden tuned to a frequency of 70 megahertz. And this is actually pointing and tuned to the frequency of Radio Poland. And the reason is that we can actually use the transmissions of Radio Poland, which are going on all the time, to actually see meteors occurring over the North Sea at a height of between 80 and 110 kilometres. You can see here the radio waves are bounced off the meteor to my receiver in the United Kingdom, and we can hear a brief snatch of Polish radio above the receiver noise. Listen to this tape. Those two species of conversation in Polish, my Polish isn't very good, but I know it is Radio Poland, tell us that a meteor occurred over the North Sea. And if we connect a chart recorder to the receiver, you can see these spikes here, which are actually meteors occurring and being picked up by the reflection of the radio waves from Poland. So by this means, we can actually see meteors even during the daytime, even though we can't actually see them visually. Now, meteors from the Jacobinids are, of course, a very young stream. We have, of course, middle-aged streams. And in a middle-aged stream, the dust spreads all the way round the orbit. It's no longer confined close to the comet, and it forms a complete loop round the comet's path. And the Earth goes through it every year. And although the stream only lasts for perhaps a day or so, we do see meteors every year. And one of the best examples is the quadrantids, which are visible every January. And because the stream is narrow, the meteors are not always the same intensity every year. For example, in 1970, we saw about 160 meteors per hour at maximum, as shown by this graph. The axis along the bottom of the graph is a number, those numbers are solar longitude, which is a measure of time used in meteor work. And in fact, the peak is only 19 hours long on January 3rd, 4th. The following year, in 1971, the meteor rates were lower, only about 100 meteors per hour. And the reason for this is that the orbit of the particles is being swung from side to side by the gravity of the giant planet Jupiter. And this means that the Earth doesn't always pass right through the centre of the stream. You can see here the tube of material left behind by the comet, and in 1970, the green line, the path of the Earth through it. We went right through the centre and rates were high. The following year, we passed slightly away from the central core and the rates were lower. And the result was that we didn't see quite so many meteors from the quadrantids.
Can we ever miss completely?
At the moment we can't, but in about 250 years from now, it may be that we will no longer intersect the stream and then the quadrantids will be lost forever.
I'm sorry about that. What about older streams still?
Well, of course, with the older streams, the particles spread all the way around the orbit, but they get steadily broader and broader. And the period of activity lasts not just for a day or so, but for a period of 2 or 3 weeks. The best known example is perhaps that due to Halley's Comet. The stream of debris by Halley's Comet is unique in the fact that the Earth intersects it at both nodes, not just one. In May, we pass through it and we get the Eta Aquarid stream, best seen from the southern hemisphere. And 5 months later, we go through the stream again and we get the October Orionids seen from the northern hemisphere. And both streams are debris from Halley's Comet. And of course, the best-known example of the old streams is my particular favourite, the Perseids in August.
And we do know the Perseid comet.
We do. Comet SwiftTuttle, seen in 1862, was a nice comet. It was visible with the naked eye. And this drawing here shows the dust fans stretching out from the nucleus. It must have been a nice comet. And at the time, it was assigned a period of 120 years. But there's a bit of a mystery here, because we expected it back in 1982, and it wasn't seen. And it may be that Comet SwiftTuttle is identical with Comet Kegler, seen in 1737, and really has a period of 130 years, and so will be back in 1992. We shall just have to wait and see.
I think we've missed it. What do you think, John?
No, I actually think it will be back, but we can't be certain.
Got to wait and see. But meanwhile, Even though we may not know where the comet is, we're quite certain we are going to have Perseids. And this year should be a particularly good one. Because obviously, if the maximum of the shower occurs during full moonlight, then the moon drowns all but the brightest meteors. And this doesn't happen this year, because the maximum of the shower is early on August the 12th, that's to say the night of 11th to 12th, and at that stage the moon is new. And here we can see a graph. The activity is now working up, as you can see, and with any luck at all, on the night of the 11th, 12th, we should have an hourly rate of something like 80 meteors visible with the naked eye. Now, how can you tell whether a meteor is a Perseid or not? What you've got to do is to find out its track. If you know your star patterns, well, that's fairly easy. You can put it on the star, on the star chart. Even if you don't, there's a very good way to do it, and that is simply by using a short stick. A foot rule does quite well. Here again, we have our all-sky picture. There to the top is Cassiopeia, and you recognize Perseus. Suppose you see a meteor. What you do is to hold up your foot rule, whatever it may be, against the sky and track where the meteor went. And if you're not certain of your star patterns, you can put it on your star chart afterwards. You then plot the trail backwards, so to speak, and see whether it came from the Perseid radiant or whether it didn't. If it did, then presumably it's a Perseid. If it didn't, well, obviously it's not. And there are sporadic meteors around, and also a minor shower in activity at the same time. But more than that, if you get the path of a meteor accurately, and so does another observer some miles away, then we can actually get the height of the meteor, and that's very valuable indeed.
It is. This is called triangulation. Now, with a triangulation, the best results are obtained with photography, because with photography you obtain the paths very accurately against the background stars. And because meteors occur between 80 and 120 kilometres above the ground, if you take a photograph of the same meteor from places separated by 30 to 50 kilometres apart, you will see them against different background stars. Here we see a camera at place A and one at place B. They will see the meteor in different parts of the sky, and by measuring the angles A and B, we can determine the start and end heights of the meteor. And this gives us a lot of information about the path of the meteor through the atmosphere.
Now, John, the question that everyone's going to ask, I think, where exactly do we look for Perseids?
Well, we're very fortunate because apart from the fact that it's new moon this year, and it's very dark, the Perseids, being an old stream, have a period of activity lasting almost 3 weeks. And even in Britain, we can't have 3 weeks of cloudy nights, so I'm sure we're going to see some. The activity curve rises, reaching a peak on the early morning hours of August the 11th, 12th, just before dawn on the 12th. And if you go out at that time, you'd be very unlucky not to see a number of Perseid meteors, many of which are bright. Now, if you look over towards the eastern sky at about midnight, you will see Perseus and Cassiopeia and the square of Pegasus rising. And in this diagram, the radiant of the Perseids is marked by that cross towards the top of the picture. Now, Perseid meteors will radiate out from that point, but you don't have to look in Perseus itself. Perseid meteors can be seen in many different places. There's one in between Aries and Andromeda, for example. And I often find that if you look in the square of Pegasus or near to the pole star, you'll be particularly fortunate in seeing a number of Perseid meteors.
Well, I think amateur photographers are going to be on the lookout. What film do you recommend and what exposure?
I would think a fast black and white film, about 400 ISO, loaded into your camera. Keep the shutter open for a time between 10 and 20 minutes, depending on how much street lights you've got, and just hope that a bright meteor crosses the field of view.
And on the whole, you're going to have a pretty good chance.
We are, yes.
Well, John, as I say, this is a particularly good year for Perseids, and of one thing we may be quite certain. We may have a period of cloudy skies. I sincerely hope we don't, but we should, as you say, have some clear periods. And even if the skies fail us, well, we have been quite certain that the Perseids themselves won't, because they come back every year, and 1988 is going to be a particularly good year for them, weather permitting. And so, we hope for clear skies, and from John and myself, good night and good viewing.
On BBC Two at 4:20 next Saturday afternoon. But now